So in this section, 8.2, now we get to current. So basically making charges flow down a wire, making electrons flow down a wire. And current is the rate that that flow is happening. Kind of like the rate of water flowing down a pipe, the rate that charges are flowing down a wire. Or the amount of current would just be the amount of charge flowing past a point divided by the time taken. So the amount of charge divided by the time taken. This would be measured in coulombs. This would be measured in seconds. So as long as you plug in coulombs and you plug in seconds, your amount of current would come out in units of coulombs divided by a second. Now, we just happen to choose to rename that to also call it an ampere, or everybody just says amp. So instead of saying 5 coulombs per second, you could just say it's carrying 5 amps. Let me try a different animation. So I put a battery down, drag and drop a wire on there. And how about I also put on a light bulb? All right, so I hooked the top of the battery to one part of the light bulb. The other part of the light bulb hooks up to a switch, and then that goes back to the battery. Now, if I close the switch, that will make a complete loop, a complete circuit, and that will allow the charge to flow. So you can see the red arrows here indicating the flowing charge, indicating the current. I could actually put in a current meter called an ammeter in here as well, instead of this wire perhaps. Right, so right now it's got a current of 0.25 amps flowing through the whole circuit. I tend to think of the battery as a pump, and the battery is pumping it through the circuit. And in order for it to keep pumping, like in order for a pump to keep pumping water, it needs water to pump. So it has to complete the full circuit so it can come back, so the battery can keep pumping. If I were to open up that switch again, the current can no longer flow. The battery can no longer get more of it to pump all the way around. You need to be able to have it be a closed circuit, a closed switch. So there are different types of material that allow electricity to either flow well or not flow well at all. And so we could call them electrical conductors when they easily allow charges to flow through them. And metals and salt water easily allow charge to flow. So we could call those electrical conductors. Electrical insulators are materials that don't easily allow current, don't easily allow charge to flow through that material. Air and rubber are good examples of electrical insulators. You ever notice like you put your hand by an outlet and the electricity doesn't jump from the outlet through the air to your hand? It's just because air is a good insulator. Semiconductors are kind of in between a conductor and an insulator, and you can kind of tweak them then to do cool things, like be LEDs or diodes. And then a superconductor allows current to flow like perfectly well. So if I imagine a conductor, it easily allows the flow of charge, but I imagine that there's still a little bit of resistance, right? Because things aren't perfect, and there's usually like a little bit of friction. A superconductor doesn't have that. It is ideal. It is perfect. It allows current to flow with like zero resistance. You could imagine it like zero friction. So let's change this light bulb then, and maybe imagine changing it to a different type of material. Let's change it to something that would have a bigger resistance. Something more like an insulator. An insulator has a high resistance. It doesn't let the current flow through. And then close the switch. There's very little current, 0.03 amps, probably not enough to light up the light bulb. But what if I was going to reduce the resistance of that light bulb material and let the current flow through there easily? Then the battery would have an easier time pumping the current around the loop, and it would pump faster. So we'd have 0.5 amps. And you notice these little lines around the light bulb here indicating that it lights up. Let's reduce the resistance even more. As you reduce the resistance, you're imagining changing the material in the light bulb. It lets the electricity flow through easier, which lets the battery pump it through faster. So now it's up to 5 amps and this light bulb is glowing bright. Now a short circuit basically means that the battery is pumping electricity through a circuit with 0 resistance, which would be a very, very, very high current. And that would actually start the battery on fire. So if the battery has a short circuit, a circuit with like 0 resistance, it's going to be working so hard to pump as fast as it can, and it just can't keep up. It starts itself on fire. One thing I could mention right here, because it's handy, is that resistance is measured in something called ohms. So if it's a conductor, it would have a low resistance, like maybe 0.1 ohms or 5 ohms even. But if it's an electrical insulator, it would have a huge value for resistance, 100,000 ohms. All right, so if you ever start to get confused by these new units, resistance is measured in ohms, current is measured in amps, and we're about to introduce a new one here, the volt. So ohms describes the resistance, how easy it is to get the current through the wire. So in this cartoon, the ohm cartoon figure here is the one that controls like the thickness of the wire. You know, how easy is it to get through this wire or this pipe? And then the amp is actually the flow through the pipe, the flow through the wire. So that's our little amp, our current person here in the cartoon in green. Now there's one more piece that we need to understand, like how the current is going to go through the wire. Not only is there current going through the wire, not only how resistive is the wire, is it easy or hard, but also how hard is the battery pushing through the wire. And that's the volt. Kind of a layman's way of thinking about it is volt is like how hard the electricity is going to be pushed or pumped by the battery. So like a battery with a higher voltage would be able to push or pump the charges through the wire harder. So if I go back to my animation here, and I'm going to leave everything alone right now. I'm going to leave the light bulb alone. I'm going to leave the wires alone. I'm going to leave the switch alone. Let's just look at the voltage of the battery. So right now it is set at 2.5 volts, and that's a property of the battery. If you go and get a battery in your house, you should be able to pick it up and read it, and it'll probably say something like 1.5 volts. And that's for AA or AAA. The rechargeable batteries are actually 1.2 volts. And a 9-volt battery it's a 9-volt battery. And the lithium button batteries are usually 3 volts. All right, so what would happen to this circuit if I reduce the voltage? Reduce how hard the battery can push the charge through this circuit. So the battery can't push as hard, so the current slows down. And in this case, that also means that the light bulb would get dimmer. So this cartoon I find really, really handy when you're learning about these different ideas and to keep them straight. But to put this in math, in an equation, which might help you learn the idea as well, let's do Ohm's law. So this right here is called Ohm's law. And it basically says that the amount of current that you're going to get depends on the voltage. And I labeled it here as a voltage difference, basically the amount of volts between the top of the battery and the bottom of the battery. All right, but it would just be the volts of the battery that you could plug in here, 1.5 volts. And then the resistance of the wire or the resistance of the circuit. Actually, I'm going to change that to say circuit. And instead of saying circuit, you could imagine just saying loop, resistance of the loop. So if you know the voltage of your battery, you plug it in the top. If you know like the resistance of your light bulb, you could plug it in down here. And when you do the division, you get the amount of current. And I know if you plug this in volts, and if you plug this in ohms, you get units of amps, units of current in amps. These are all SI units. As long as you plug in SI units, you get your answer out in SI units. Volt is often just abbreviated with a capital V, so you should be able to find that on a battery, no problem. Amps is usually just abbreviated with a capital A. And ohms is abbreviated with a Greek omega, which usually isn't listed on stuff that you'll find around your house. So Ohm's law is not valid in all cases. It is only for certain materials or certain objects. Like, you can use Ohm's law on wires and incandescent light bulbs. That's the old-fashioned light bulbs, the ones that we should not be using anymore because they waste so much energy. But you cannot use Ohm's law on LED bulbs, the new kinds, the energy-efficient kinds. Certain things called capacitors, which you might not know what that is, and that's fine, or diodes, and a bunch of other things as well. Ohm's law is only for certain materials. Batteries are a constant voltage device, at least until they're dead, DED, in meme speak. Right? They're a constant voltage device. So a AA battery would give you 1.5 volts. It doesn't matter if you hook it up to 100 light bulbs or 1 light bulb. It's still going to be pumping at 1.5 volts. Now, it may be able to get a lot of current through, or it may not. If you hook up 100 light bulbs in a row, you're probably not going to be able to get any current through just because it's so hard for the battery to push through all 100 light bulbs. But no matter what you hook up to it, it's going to be trying to pump at 1.5 volts. Now, electricity is something to be safe with. And until you know what you're doing, it's best to be extra safe. And here's one reason why, if nothing else, be around electricity with dry skin. So let's figure out the current that might be able to flow through your body if you touch two ends of a 12-volt battery, kind of like a car battery. Now, have you ever hooked up jumper cables to a car battery and you touch the red and the black cables together? You get a lot of sparks. It looks really dangerous. Let me see if I can find a video of that real quick. There you go. So let's say you have some jumper cables hooked up to a car battery and you use the other end of the jumper cables and you basically short the circuit, touching the two cables together. You can get some bright, scary looking sparks, which happens because there's a high current. But maybe the car battery is rather, instead of just going through a wire, also is going to have to try to go through your wet skin. Let's say you had wet hands and you touched both ends of the car battery. Wet skin only has a resistance of about 1,000 ohms. So if you do 12 volts of the battery, trying to get through your 1,000 ohm resistance for wet skin, that ends up about 0.012 amps. Now, if you look this up, what would that feel like to a person? That would be a painful shock, but not lethal for most people. Like if you had a pacemaker or a heart condition, yes, it could still be lethal. Now, if you had dry skin tends to have a resistance more like 100,000 ohms. So a 12-volt battery divided by 100,000 ohms trying to get through your dry skin, the current that it would be able to push through your body would be 0.00012 amps, so much, much smaller. And you look it up in a table, is that something a human can even feel? And you probably can't even feel it. All right, so what I have here is a multimeter, basically meaning that it can measure voltage, resistance, and current. So first of all, go away, cat. So first of all, how about we measure the voltage? I'm going to do DC voltage because this is a battery. And check the voltage on this 9-volt battery. And it doesn't really matter which order you have these in. It'll just read positive or negative if you have them flipped. So it is, well, it's only reading 5 volts right now, meaning it's almost dead. So this is a 5-volt battery. And if I had the probes switched, it would read negative 5 volts, but still 5. Now, if I just touch both ends of these, it's trying to pump electricity through my body, but it's not doing a very good job. The current is so low, I can't even feel it. If I were to lick the ends of these, it tingles. Right, but it didn't hurt, it just tingles and tastes funny. If you wanted kind of a fun, safe way to learn about electricity and circuits, I highly recommend this toy. You just really search for snap circuits. And I bought a kit and I gave it to, what was he, my 5-year-old at the time. And he would just follow the pictures. It tells you how to hook stuff up and talks you through it. You just follow the pictures, and ever since then I've just kept buying the add-on kits and eventually even bought some more advanced stuff. And right now he's better at circuits than I am. And the great thing about these this kit is, like, you could short out a battery and start it on fire, but there's actually a hidden little element in here, a hidden little resistor that doesn't let that happen. So you can't even short these out. It's pretty darn safe, which is why I gave it to my 5-year-old. One really frustrating fact when you're trying to learn circuits is that the electrons, which are negative, and they're what's flowing through the wire to make electricity, they move from the negative end of the battery around the circuit, like through a light bulb, and then they end up at the battery at the positive end. Before we knew it was the electrons moving in the wire, we guessed that it was the positives moving through the wire. So we describe current as moving in the opposite direction. So we describe current as going from the positive end to the negative end. You can see that we draw the currents and by these red arrows here flowing from the positive end of the battery around the circuit and into the negative end of the battery. But realistically, what's actually happening is the electrons are what's moving from the negative end of the battery through the circuit and back, kind of getting sucked into the positive end of the battery. And it doesn't really matter which mental picture you use to describe electricity, they both work. There's a couple of different ways that you could calculate the electric power, like the rate that it's using energy. And you could do that by finding an object's current and its voltage. So like if I were to, if I was to know the voltage of, say, a battery and the current that was going through a circuit, I could figure out the power that that battery was putting off. And when you do this in volts and amps, the power comes out in watts. Now, I just bought a pack of LED light bulbs, and I know that my LED light bulbs were listed as using 10 watts of power. And I'm going to plug it in to 120 volts. That's what US standard electricity is 120 volts. So I guess what I could do then is figure out the current flowing through the light bulb when it's on. So let me just rearrange that real quick. Divide both sides by voltage. These cancel out. So the power was 10 watts. Divide by the voltage of 120 volts. And I get 0.083. And I was doing watts, which is SI units, divided by volts, which is SI units. And now I'm getting a current, which is going to be in SI units, and we call that an amp. So 0.03 amps going through my LED light bulbs when I turn on my lights in my house. All right, there's another equation that you could use to find the electric power being used by a light bulb, or the electric power being pushed out by a battery. And you would use this version if maybe you know the resistance of the object instead of the voltage. And both of these equations work, they're kind of redundant. You just pick whichever one is more useful. But again, if you put everything in SI units, so in this case the current is amps, and then you'd have to square that, and you plug in ohms, a certain number of ohms for resistance, and you would get your electric power, which would again be in watts. The last thing we should do is, kind of clarify what AC versus DC is. Now, the electricity in your wires that you get from the power company, that is AC. The electricity that comes from batteries is DC. And modern electronics need DC. So that's why your laptops and TVs and stuff usually have some sort of kind of brick that gets plugged into, because the AC comes from the wall. This has some circuitry inside of it. It changes AC electricity into DC electricity, and then that can go to your computer or your laptop or a TV. Right? So I usually just call this a converter, but you can feel how it's warm. Right? It is wasting power in the form of heat, which in the winter I don't mind because it's heating my house anyways. But in the summer I do mind because I'm having to pump that heat out with the air conditioner then. Let's actually cover AC versus DC then. All right, in order to show you AC, I have to download a Java simulation, and so I want to do that. I'm going to keep it because I trust this website. I've used it for years. All right, and it's through the University of Colorado. And then I open it up. So before we had the DC, and you were able to see the current flowing through that. So now I'm going to put an AC source on here, connect it to a wire, connect it to a light bulb, connect that to a wire. I'm going to have to make a full circuit again. Let's put a switch in here. All right, so DC, which is what we did before with the batteries, basically means direct current. And here is AC, and AC stands for alternating current. So can you just see the difference? The light bulb is pulsing on and off, and that's because there's current and then it stops, and then it reverses the current and goes backwards and then stops. And the light bulb will only light up while the current is flowing. So an alternating current is more like, instead of just a battery, which is push, 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 and pumping the current in the same direction, an alternating current is a push and a pull through the wire. So that's what we get from the power company. The power company pushes the electrons through the wire and then it pulls them back. And it pushes them forward and it pulls them back. And we can still use that as electricity, right? Because it's the motion of the charges that we can use to do work and light bulbs. All right, if I was going to show you a voltage chart of this, and like before, the battery was just like 1.2 volts. Wall electricity is different. It fluctuates between a positive value, 0, negative value, and back and forth and back and forth. All right, so right now what this is doing is alternating back and forth between negative 10 volts and 10 volts. Wall electricity pushes harder than that. Wall electricity is 120 volts. It pushes and pulls back and forth with 120 volts. Which is one reason why this multimeter of mine has so many settings, because it can measure DC voltage, but you have to change it to a different setting for AC voltage. You can measure DC current from like a battery or like a laptop or something, or AC current. All right, if you stick these into a wall outlet to actually see if the voltage is right, you would set it to AC voltage and then stick these into the outlet. I would suggest only doing that after you've had some other practice with less dangerous things though. Especially don't be sticking these into wall outlets unless you know exactly which holes your wires should be plugged into. It is okay to do that if you have them plugged in to measure voltage. It is not okay to do it if you have it plugged in to measure current, because then it will make a short circuit. If you wanted to watch a video about 25 minutes long, kind of explaining how the United States electrical system works from like the power grid to your house and how you can have 120 volts and 240 volts. I like this video by Technology Connections, and it's just on YouTube if you search for it. The title of it is "The U.S. Electrical System is Not 120 Volts."